So we have two really important for actually both physics and math applications of integrals of that type. One is the so-called Stirling approximation. You'll see this in thermo a lot. And now that we have a continuous representation of n factorial, what you can do is you can evaluate a whole class of integrals that look like this, and they actually show up fairly commonly. And secondly, there's an idea of a saddle point approximation. So a saddle point approximation is every once in a while you'll end up with this gross integral that looks essentially like this. So the active ingredient is something that looks like this. Yuck, you have a function in the argument of an exponential. So this is a candidate for saddle point approximation. And this is the starting point for Stirling's approximation. And Stirling's approximation is an approximation of large factorials, which shows up in statistical mechanics a lot. So, which one to do first? Let's do, they kind of both show up together. So the idea of the saddle point approximation is essentially that you can represent the function itself by its Taylor series, and its Taylor series expansion for anything that's well behaved enough to actually have an answer should terminate at the quadratic term. So actually, I think the best thing to do is to do saddle point first. So we'll do saddle point expansion first. Okay, so let's say that we have an integral of this type. So we've got integral over some interval, e to the n f of x dx. Where n is just, maybe alpha would be a good choice too, but n is just some parameter that basically tunes how big f of x is, or it's something that we can factor out from all of the terms in f of x. So there are two possibilities. Possibility one is that f of x has a global maximum on the interval, which is to say, if I plot f of x versus x, it's going to look something like this. So here's my interval over which I'm integrating. Okay. And the interval could be anywhere, could be the entire real line. Okay, if f of x does not have a global maximum, which means it's unbounded, then we're essentially going to have e to the infinity, right? So the other option is integral does not converge, so we don't even care. So that's kind of an angels dancing on the head of pins math class question. So this is not something that we would worry about. Okay, so let's say that f of x does have a global maximum on the interval I, therefore it does exist. What's going to be true, because the exponential is going to be dominated by the behavior of this region around the global maximum. So essentially the exponential is like, pouring kerosene on a fire for the behavior of f of x. So it's going to be completely dominated by the region around the global max. So that's going to be bigger than everywhere around it. And then I'm taking the exponential on top of that. So basically, this is all an argument to saying that a really good approximation of this entire integral is going to be just the region around the global max. And how do we represent approximations of functions over some region? We use Taylor's theorem. So we'll take a Taylor-Maclaurin series. So this is going to be good enough. So x naught will be the region where this thing, or the point at which this thing has a max. And then at the max, I'll write down the term, but this is going to be 0. Because at a maximum, the first derivative vanishes. Got 1/2 there. So we have a value, and then we have a second derivative, and this is going to be the most important term. So technically, this should be delta x cubed. So this value itself is small, like the deviations from x naught. And x naught is the value at which the function inside of the integral with the exponential is a maximum. So we just replace it, and then what you realize is, hey, this looks exactly like the type of integral we just solved on our way of proving or evaluating what gamma of 1/2 is. So any questions about the argument that went into this? So there are definitely like benchmarks and criteria you can put on how good your saddle point expansion is. But the argument itself is that if you have a function inside of an exponential, either the thing goes to infinity and your integral doesn't exist, or you can represent the thing really well by just the parabola in the region around the max. So that's kind of what we're saying, is that after you take the exponential of this, this is going to be most of the contribution to the integral. Okay, okay. So what we have is, again, just write the whole gross thing. So the whole integral then looks like this. The two hashes are two derivatives. And again, up to some nasty kind of rewriting, this is the thing that we just solved. So I'll kind of leave it to you guys to show this, but this is equal to 2 pi. You now know where the 2 pi comes from, n f double prime factorial evaluated at the maximum, e to the n x naught. Okay, so what this last term is this is what you would get by just factoring the exponential, right? So the sum of two terms in the argument of the exponential, you just pull this f down, and then the rest is from precisely the thing that we just evaluated, the same type of integral. Okay, so this is called a saddle point expansion. Saddle point expansions, honestly, I do not remember this formula and cannot remember it to save my life. Every time I have ever needed to take a saddle point expansion, I have kind of re-derived it on the spot or looked it up, and that works really well because the argument is like pretty straightforward. So if you ever in your life end up with an integral that has a function inside of an exponential, it should immediately say saddle point expansion. So yeah, here's the formula, but honestly, just kind of re-derive it. Okay. So the most famous example is Stirling's approximation. Oops. Of n factorial for large n. And we have n factorial is equal to integral over the positive real line, e to the minus t, t to the, no, call it x. Yeah, whatever, t is fine. X to the n, t to the n, e to the minus t dt. Okay, what does this have to do with the saddle point integral? Is I'm going to write this in a way that looks kind of silly at first. And what I have is rewriting the t term, so everything can go in the exponential. I get n ln t minus t dt. So that's just rewriting stuff. Okay, and then lo and behold, we have something that looks like we can saddle point it. So we're not quite there. We need to do one little substitution. So we're going to define n times t. Oops, the opposite way. So this doesn't quite look like the formula where an n is in front of everything. So we'll define a new variable y, which is equal to n times t. And then with that, we have this in a suitable formula. So factoring out some stuff that turns out to be constant, and then, aha, we have an n out in front of everything, dy. We can factor out all of this stuff. The integral is over y. So e to the n ln n times n. And then integral stuff that does depend on y, which is in saddle point form. So this is a good exercise, but I'll just say, like, look, we've got this formula. I'll just dump it in here so you at least know where the weird pi stuff comes from. But then this is the active part. So a lot of times you'll actually see Stirling's approximation as n factorial for large n is proportional to n times n to the n. And that's the kind of active ingredient. So this is what you'll often see as Stirling's approximation. This will give you another factor of another term which is not of the same order as the leading term n ln n, but it exists. So this, we get 2 pi, so that's the Stirling part, or the saddle point part, and then n over e to the n. And a lot of times you just see this as n factorial is proportional to root n to the n. Or the weird logarithmic way of writing it. So who cares? Well, I do because I don't want to do this. So 50 factorial, which, you know, you can actually compute this. It is possible. It's like 3.04 times 10 to the 64th. So it gets up there. And then if I were to use my approximation of 2 pi root n, so this saddle point approximation, n over e to the n, easier than recursively doing the 50, that is equal to 3.03 times 10 to the 64th. So the numbers they get, you know, 10 to the 64th is pretty big, and we're off by like 1/3 of 1%. So that's actually not bad, right? Okay, so any questions about any of that stuff? Okay, so this would be a good place to stop and let you guys do some stuff. I'll define a thing and then we'll do some problems with it, and then you can, you know, essentially like warm up for the homework problems.